All right, so temperature and thermal energy. When we mix two items together, let's imagine putting a frozen metal cylinder into a glass of water. Well, what's going to happen with the lukewarm, maybe water, the frozen cylinder is placed in there, it's going to decrease the temperature of the water. Well, we can actually calculate a couple different things with that scenario using this study of calorimetry. I'll talk about those terms in a minute. But remember, energy can't be created or destroyed. So the energy is absorbed by maybe metal, and the energy released by the water have to add to zero. Energy can't be created or destroyed. It's moved from one object to another. So if both these energies were heat energies, Qs, then the heat energy of maybe item A, which could be the water, plus the heat energy of item B, which could be the metal cylinder, have to add to zero. So if that's the case, then we can come up with a nice little formula. Q is equal to MC delta T. Delta T is final minus the initial. If we do that for both, we have this nice little formula right here that we can use mostly for calculating the specific heat of an item, maybe like that metal that's frozen that we just put into a cup of water. We calculate the specific heat of that metal. Now, if we solve this for the final temperature, if we solve this formula, we would have to distribute the MCs into this binomial, distribute the MCs. If you want some entertaining math, then take the next 5 minutes and derive this formula that I have down here. You have to collect like terms, get to TF, the terms with the TF on one side, and divide by the coefficient of the TF, and you end up with this fraction down here. This fraction is going to be used to calculate the final temperature. So we have two formulas we got to figure out. We're going to do a couple problems on that. Before we do it, though, let's talk about these terms. Calorimetry is the experimental measurements of thermal energy transfers using a calorimeter. Now, calorimeter is the thing you do the experiment in. It's an isolated system trying to keep the energy of the outside the system away from the system. And this isolated system is used to determine the quantities of thermal energy transferred. So this is a temperature thermometer in here. Oh, that's like a little cylinder placed in water. Inside this is like an air gap, trapped air, best way to insulate an item, trapped air. But this is a calorimeter. This is a pretty sophisticated looking calorimeter. We use little simpler ones in the classroom. We use styrofoam cups, get similar results. But anyhow, let's look at a problem. Let's take, for example, a metal cylinder with a mass of 105 grams, and it's at a pretty warm temperature, and it's placed in water that's cooler. So you got a hot metal cylinder placed in the cooler water. And they stir it for a little bit and find out the final temperature of the mixture is 43. And now the question asks, what is the specific heat of the metal? Well, if this is the metal's data, we got the initial mass of the metal is 0.105, 105 grams. The next item on our formula is C. All these sub A's are item A. We're going to call item A the metal cylinder. So we got the C. We don't know the C for the metal cylinder. That's what the question says. What's C? Specific heat symbol is C. What is the C for the metal cylinder? We don't know it. That's what it's asking us to find. So what's the final temperature? Well, that's going to be the same for both. That's 43. And the initial temperature of the cylinder. The cylinder initial temperature 75, minus 75. Now plus the mass of the water. So everything after the plus and before the equals is talking about the water. So the mass of the water is 0.352 kilograms. The next thing we're multiplying that by is the specific heat of water, 4180 off that chart. We know that from the chart, 4180. And then parenthesis, the final temperature, which is 43 again, minus the beginning temperature of the water, which is this 37 number. So now, one of these binomials are going to produce a difference that's negative. 43 minus 75 is going to be negative. And this one, 43 minus 37, is positive. So this negative 32 If we add that whole entire term to both sides, it becomes a positive term. Over here, what a positive 32. The other thing you got to note here, these two minus and get 6, so this is the same as that. This guy being negative goes to the other side. The other thing is the difference in the temperature for degree C, the change. The difference on the Celsius scale is the same as the change on the Kelvin scale. Remember, it's a 1-to-1 scale, so when you're talking about a delta T, the units degrees C and K are interchangeable. So now we have this formula, and we could go straight to our calculator. This times this times this, divided by 0.105, divided by 32 to get 2600 to 2 sig figs, it looks like. Why 2? Oh, this guy's 2. So the specific heat of the metal is 2600 joules per kilogram Kelvin. Let's look at another example. Number 2. Well, it's all worked up for you. Let's see if we can make sense of it. I might have to use the marker. All right, here we go. I got a little marker trail. This is a little slow here. But all these items right here, oh, is that fat? I might have to thin that up. How do I thin it up? Let me try to thin her up. Come on, thinner. Thinner. I don't know what thinner is. I can't thin it up, so we're going to have to go big fat. Big fat marker. So this big fat marker is going to do the job. Everything right there, let's say, is referring to one of the items. Let's say that is going to be the zinc. So these are the characteristics of the zinc. Let's go to a different color. How about blue? You like blue? Let's go blue. Blue items right here. All these blue items are referring to what is the other item. So that's going to be water. So let's see if we can make sense of it. Notice the division bar goes the whole way through though, and you got to add on the top first and then the bottom. So another thing you want to note is the question says, what is the final temperature of the system? So we want to use the TF equals. Final temperature of the system is the mass of item A, which is going to be the zinc. What's the mass of zinc? The mass of zinc is right here. No, what is it? Right here. This is, yep, mass of zinc. So I'm just going to go to red. Let's go red. So this is the mass of zinc. This is a mass of zinc. Zinc's, where's zinc's number on here? Zinc. We got to find zinc. Oh, there it is right there. So 388 would be the second thing here. And then this is the beginning temperature of the zinc, which is right here. It looks like 115. All right, let's go get a blue dot, dude. Blue dot, blue dot. Blue dot's going to be for the water. So the water starts at 0.50. Water's specific, oh, right there. Water's specific heat, that's C number. And then water's beginning temperature is 0.15. All right, so let's see if we can get them all into the chart right. So we need the mass of zinc, and that's 0.040. We need the C of zinc. Oh, that's on a chart, 388. And we need the beginning temperature of the zinc. Oops, starts at 115. So we got the 115. Now notice these two carry down. They carry down to the bottom. They're the same. Everything on the left side of the pluses refer to zinc. Everything on the right side of the pluses refer to the water. So let's go with the mass of water. The mass of water is this 0.50. Then the next item is a C, specific heat of water from the chart, 4180. The beginning temperature of the water, is 15 degrees right there. And then again, these two carry down, just like in a formula. These two M's and C's carry down. So now, how do you simplify something as massive as this? Well, change each expression, each product into a number first, then add, then divide. So when you're using a big fraction, change each product. You should end up with 4 numbers just like this, 1800, 31,000, 16, and 21. Those are the results according to sig figs. Then you add the tops to get this number, and then you divide, working sig figs the whole way through. You get 16 degrees C. 16 degrees C. So the change in temperature, or no, this is what is the final temperature of the mixture? 16 degrees C.